Deep Learning Foundations and Concepts. 1. The Deep Learning Revolution. 1.3. A Brief History of Machine Learning. Introduction. Machine learning has a long and rich history, including the pursuit of multiple alternative approaches. Here we focus on the evolution of machine learning methods based on neural networks, as these represent the foundation of deep learning and have proven to be the most effective approach to machine learning for real-world applications. Neural network models were originally inspired by studies of information processing in the brains of humans and other mammals. The basic processing units in the brain are electrically active cells called neurons, as illustrated in Figure 1.12. When a neuron fires, it sends an electrical impulse down the axon where it reaches junctions, called synapses, which form connections with other neurons. Chemical signals called neurotransmitters are released at the synapses, and these can stimulate, or inhibit, the firing of subsequent neurons. A human brain contains around 90 billion neurons in total, each of which has on average several thousand synapses with other neurons, creating a complex network having a total of around 100 trillion synapses. If a particular neuron receives sufficient stimulation from the firing of other neurons, then it too can be induced to fire. However, some synapses have a negative, or inhibitory, effect whereby the firing of the input neuron makes it less likely that the output neuron will fire. The extent to which one neuron can cause another to fire depends on the strength of the synapse, and it is changes in these strengths that represents a key mechanism whereby the brain can store information and learn from experience. These properties of neurons have been captured in very simple mathematical models, known as artificial neural networks, which then form the basis for computational approaches to learning. Many of these models describe the properties of a single neuron by forming a linear combination of the outputs of other neurons, which is then transformed using a nonlinear function. This can be expressed mathematically in the form where x1 to xm represent n inputs corresponding to the activities of other neurons that send connections to this neuron, and w1 to wm are continuous variables called weights, which represent the strengths of the associated synapses. The quantity is called the pre-activation, the nonlinear function f is called the activation function, and the output y is called the activation. The simple mathematical formulation given by 1.5 and 1.6 has formed the basis of neural network models from the 1960s up to the present day, and can be represented in diagram form as shown in Figure 113, single-layer network. The history of artificial neural networks can broadly be divided into three distinct phases according to the level of sophistication of the networks, as measured by the number of layers of processing. A simple neural model described by 1.5 and 1.6 can be viewed as having a single layer of processing corresponding to the single layer of connections in Figure 1.13. One of the most important such models in the history of neural computing is the perceptron, in which the activation function f is a step function of the form. This can be viewed as a simplified model of neural firing in which a neuron fires if, and only if, the total weighted input exceeds a threshold of 0. The perceptron was pioneered by Rosenblatt, who developed a specific training algorithm that has the interesting property that if there exists a set of weight values for which the perceptron can achieve perfect classification of its training data, then the algorithm to find the solution in a finite number of steps. As well as a learning algorithm, the perceptron also had a dedicated analog hardware implementation as shown in Figure 1.10. A typical perceptron configuration had multiple layers of processing, but only one of those layers was learnable from data, and so the perceptron is considered to be a single-layer neural network. At first, the ability of perceptrons to learn from data in a brain, like way, was considered remarkable. However, it became apparent that the model also has major limitations. The properties of perceptrons were analyzed by Minsky and Papert, who gave formal proofs of the limited capabilities of single-layer networks. Unfortunately, they also speculated that similar limitations would extend to networks having multiple layers of learnable parameters. Although this latter conjecture proved to be wildly incorrect, the effect was to dampen enthusiasm for neural network models, and this contributed to the lack of interest and funding for neural networks during the 1970s and early 1980s. Furthermore, researchers were unable to explore the properties of multilayered networks due to the lack of an effective algorithm for training them, since techniques such as the perceptron algorithm were specific to single-layer models. Note that although perceptrons have long disappeared from practical machine learning, The name lives on because a modern neural network is also sometimes called a multi-layer perceptron or MLP, backpropagation. The solution to the problem of training neural networks having more than one layer of learnable parameters came from the use of differential calculus and the application of gradient-based optimization methods. An important change was to replace the step function 1.7 with continuous differentiable activation functions having a non-zero gradient. Another key modification was to introduce differentiable error functions that define how well a given choice of parameter values predicts the target variables in the training set. We saw an example of such an error function when we used the sum of squares error function 1.2 to fit polynomials. With these changes, we now have an error function whose derivatives with respect to each of the parameters in the network can be evaluated. We can now consider networks having more than one layer of parameters. Figure 1/5 shows a simple network with two processing layers. Nodes in the middle layer called hidden units because their values do not appear in the training set, which only provides values for inputs and outputs. And each of the output units in figure 1.15 computes a function of the form given by 1.5 and 1.6. For a given set of input values, the states of all of the hidden and output units can be evaluated by repeated application of 1.5 and 1.6 in which information is flowing forward through the network in the direction of the arrows. For this reason, such models are sometimes also called feed-forward neural networks. To train such a network, the parameters are first initialized using a random number generator and are then iteratively updated using gradient-based optimization techniques. This involves evaluating the derivatives of the error function, which can be done efficiently in a process known as error backpropagation. In backpropagation, information flows backwards through the network from the outputs towards the inputs. There exist many different optimization algorithms that make use of gradients of the function to be optimized, but the one that is most prevalent in machine learning is also the simplest and is known as stochastic gradient descent. The ability to train neural networks having multiple layers of weights was a breakthrough that led to a resurgence of interest in the field starting around the mid-1980s. This was also a period in which the field moved beyond a focus on neurobiological inspiration and developed a more rigorous and principled foundation. In particular, it was recognized that probability theory and ideas from the field of statistics play a central role in neural networks and machine learning. One key insight is that learning from data involves background assumptions, sometimes called prior knowledge or inductive biases. These might be incorporated explicitly, for example by designing the structure of a neural network such that the classification of a skin lesion does not depend on the location of the lesion within the image, or they might take the form of implicit assumptions that arise from the mathematical form of the model or the way it is trained. The development of backpropagation and gradient-based optimization dramatically increased the capability of neural networks to solve practical problems. However, it was also observed that in networks with many layers, it was only weights in the final two layers that would learn useful values. With a few exceptions, notably models used for image analysis known as convolutional neural networks, there were very few successful applications of networks having more than two layers. Again, this constrained the complexity of the problems that could be addressed effectively with these kinds of network. To achieve reasonable performance on many applications, it was necessary to use hand-crafted pre-processing to transform the input variables into some new space where, it was hoped, the machine learning problem would be easier to solve. This pre-processing stage is sometimes also called feature extraction. Although this approach was sometimes effective, it would clearly be much better if features could be learned from the data rather than being handcrafted. Deep networks. The third and current phase in the development of neural networks began during the second decade of the 21st century. A series of developments allowed neural networks with many layers of weights to be trained effectively, thereby removing previous limitations on the capabilities of these techniques. Networks with many layers of weights are called deep neural networks, and the sub-field of machine learning that focuses on such networks is called deep learning. One important theme in the origins of deep learning was a significant increase in the scale of neural networks, measured in terms of the number of parameters. Although networks with a few hundred or a few thousand parameters were common in the 1980s, this steadily rose to the millions and then billions, whereas current state-of-the-art models can have in the region of 1 trillion parameters. Networks with many parameters require commensurately large data sets so that the training signals can produce good values for those parameters. The combination of massive models and massive data sets in turn requires computation on a massive scale when training the model. Specialist processors called graphics processing units or GPUs, which had been developed for very fast rendering of graphical data for applications such as video games, proved to be well suited to the training of neural networks, because the functions computed by the units in one layer of a network can be evaluated in parallel, and this maps well onto the massive parallelism of GPUs today. Training for the largest models is performed on large arrays of thousands of GPUs linked by specialist high-speed interconnections. Figure 1.6 illustrates how the number of compute cycles needed to train a state-of-the-art neural network has grown over the years, showing two distinct phases of growth. The vertical axis has an exponential scale and has units of petaflops days, where a petaflop represents 1,000 trillion floating point operations, and a petaflops is 1 petaflop per second. 1 petaflops day represents computation at the rate of a petaflop for a period of 24 hours, which is roughly 10 power 20 floating point operations, and therefore the top line of the graph represents an impressive 10 power 24 floating point operations. A straight line on the graph represents exponential growth, and we see that from the era of the perceptron up to around 2012, the doubling time was around 2 years, which is consistent with the general growth of computing power as a consequence of Moore's law. From 2012 onward, which marks the era of deep learning, we again see exponential growth, but the doubling time is now 3.4 months, corresponding to a factor of 10 increase in compute power every year. It is often found that improvements in performance due to innovations in the architecture or incorporation of more sophisticated forms of inductive bias are soon superseded, simply by scaling up the quantity of training data, along with commensurate scaling of the model size and associated compute power used for training. Not only can large models have superior performance on a specific task, but they may be capable of solving a broader range of different problems with the same trained neural network. Large language models are a notable example, as a single network not only has an extraordinary breadth of capability, but is even able to outperform specialist networks designed to solve specific problems. We have seen that depth plays an important role in allowing neural networks to achieve high performance. One way to view the role of the hidden layers in a deep neural network is that of representation learning, in which the network learns to transform input data into a new representation that is semantically meaningful, creating a much easier problem for the final layer or layers to solve. Such internal representations can be repurposed to allow for the solution of related problems through transfer learning, as we saw for skin lesion classification. It is interesting to note that neural networks used to process images may learn internal representations that are remarkably like those observed in the mammalian visual cortex. Large neural networks that can be adapted or fine-tuned to a range of downstream tasks are called foundation models, and can take advantage of large, heterogeneous data sets to create models having broad applicability. In addition to scaling, there were other developments that helped in the success of deep learning. For example, in simple neural networks, the training signals become weaker as they are backpropagated through successive layers of a deep network. One technique for addressing this is the introduction of residual connections that facilitate the training of networks having hundreds of layers. Another key development was the introduction of automatic differentiation methods, in which the code that performs backpropagation to evaluate error function gradients is generated automatically from the code used to specify the forward propagation. This allows researchers to experiment rapidly with different architectures for a neural network and to combine different architectural elements in multiple ways very easily, since only the relatively simple forward propagation functions need to be coded explicitly. Also, much of the research in machine learning has been conducted through open source, allowing researchers to build on the work of others, thereby further accelerating the rate of progress in the field.